that's the other horn of this dilemma, which is this third strategy we have, which is the fact that as you try to implement those and emulate those different features, there are variances in how those features actually work. So if you don't get those perfectly right, you create differences that we can monitor for as well. So our talk talks about 3 different strategies of places that we're using to attack the virtualized malware. And here's one.
We think that all those strategies will encapsulate pretty much every detection method someone can come up with. And in fact, we've gone through and implemented one example from each of these to show how it works. So in terms of side channel attacks, that's something that's actually not very familiar in the IT security world, even though it's become very relevant with remote network timing attacks being mounted against real systems like OpenSSL in Apache. So basically, a side channel attack is anytime you have a system where resources, instructions, cache, power, heat, sound, all of these side channels have been used to identify when data or logic-dependent processing has been done within a processor. So, for example, here's an easy one. This would be an interview question at my previous employer, where if you're looking at this, what's wrong with this code? Well, I mean, there's a lot of things wrong with it. For instance, it takes the size of the smallest string, but also this gives the attacker a side channel where if they time the amount of time it takes to return login failed while they guess various passwords, the string comp algorithm exits early. And so that will give you information about how close your guess is to the real guess, because each time you get a letter right, it'll take a little bit longer to tell you failed. And this type of attack was found early in '83 by Lamson on 10x. It's sort of the classical example of timing attacks. But it was mounted in a much more effective way against crypto later on when Kotter my former boss, used it for attacking RSA. He basically just used a stopwatch equivalent to time an entire RSA operation, and from that he was able to distinguish the number of squares and multiplies, and thus the key that was used. And he improved this attack later on to what's called DPA, or power analysis attacks, where you actually monitor the power consumption of a smart card, which is an embedded device. You can't see the keys directly, but you can see the power consumption of this, and it varies based on the key bits. But this varying is not always easily observable, so what you do is you collect a lot of traces and average them together, and then compare a given candidate guess against the mean. And from that, you can distinguish key bits, which, when you ordinarily were looking at it, it looks like random noise on this oscilloscope. This was extended to what becomes relevant to I think, our world here, which is remote timing attacks, where Brumley and Bonnet were able to mount an attack against a real RSA implementation, an optimized one it had Montgomery multiplication and Barrett reduction and all the rest in it. But they were still able, over a WAN connection, to extract the key bits of an OpenSSL process. And this is a really important breakthrough because a lot of people were a little dubious about this. They say, oh, it matters in the embedded world, but doesn't matter in the IT world. Well, that was extended even more very recently with branch target buffer prediction timing attacks, where people could actually monitor the state of the branch prediction buffer and use that to tell if some other process running on the same CPU, for instance on another core or on the same core but subsequently, was affecting the branch target buffer, and thus they could tell what branches were taken in that code and what branches were not taken. And this is the one that's most relevant to us.
So, I mean, please, after this talk or whenever you guys get a chance, if you haven't read those last 2 papers, just plug everything but the dates, which I may have gotten wrong, into Google and pull down those papers. The Dan Bona paper, for instance, hugely important. First of all, it debunks the notion that timing attacks are difficult to pull off. But second of all, please think about the fact that what these guys did in their research project was they wrote code that pulled the RSA private keys out of remote computers using only timing differences over a wide area network connection. And we have a little bit more to say about that later on in the talk. And then the second talk is kind of the product of a long series of local timing attacks. These are attacks where you're using local chip features to attack machines. But it's relevant to virtualization as well. This is, again, the idea that if you have access to a machine that's doing crypto operations, if you're one user and there's another user doing something sensitive on the same machine, you can time microarchitectural differences, in this case, branch timing, which we'll talk about more in a little while, to extract keys from running processes. If you run an SSL server on a shared virtual host environment where other virtual hosts are running and maybe under the control of an attacker, be aware that those attackers are in an extremely advantageous position to pull the keys out of your process because they have access to the trails that are being left in the microarchitecture of the things that that secure server is doing. So it's not happening yet, but it's not an inconceivable attack that you could see general purpose tools to do that.
Right. And remember, we're here at the end, so we have local access to the machine. We're in an advantageous spot as the detector of this malware. So a common complaint is what real systems are too noisy. Hopefully, if you've read those other two papers, you'll find that real systems are not too noisy, but there are things you can do to adjust for that. So in this case, there's been a great paper that came out recently, only a few months ago, about how to optimize remote timing attacks. And normally people think you have millisecond level jitter on a WAN connection. Well, Crosby and the rest here found that on a WAN, they were able to compensate for the jitter by profiling their local computer and reducing it to about 15 to 100 microseconds resolution, depending on the situation. And on a LAN connection, they were able to get it down to 100 nanoseconds. Now remember, this is sub-ping time resolution in the processor, and it's an extremely important example of how, using statistics, you can reduce the noise that's affecting your measurements of the system.
And in crypto operations, that's really important because there's a noise floor when you're doing monitoring, right? That, the fact that you can do over a LAN 100 nanosecond profiling over a remote system opens up a wide area of attacks. But on a normal local system, we have much better precision than even this. We don't even need the statistics to do that.
Right. So there's two strategies and things we can do about this. The first one is, if there is noise and you can't get rid of it, then just take more samples and average. The more samples you have, noise is random, it's decorrelated from the actual operation you're doing. You're working, for instance, with secret key material that's constant, whereas the noise is random. Those two are different, and they'll separate into different piles when you average. And I'm simplifying the statistics a lot, but that's basically what happens. And because we have local access, we have higher resolution measurements than some of these remote timing attacks. But we also have another capability, which is we can briefly, very briefly, less than a couple instructions, execution time, we can monopolize the CPU, run a few 100 instructions, measure some microarchitectural details, and then allow the CPU to continue. And when you're looking at AV scanners, they have a much bigger footprint on your processor than a couple simple probes like this. And you can repeat these periodically and correlate measurements. But the key thing here is that eliminating data-dependent side channels, all of them, in your software is very hard. Eliminating it in your microarchitecture is almost impossible. I mean, if you have two things executing on the same CPU, there are going to be dependencies between those that are visible in the microarchitectural details. And we'll talk about how to measure those in just a minute. First, we wanted to tell you how to find your own side channels. It's really easy, but sometimes requires a little bit of cleverness in figuring out what to do with it once you have found it. So the key is, first of all, look at all the resources that your opponent is using. You have to execute instructions in a hypervisor. You can't not execute instructions. You can't build a microcode level hypervisor using VT. You'd have to do it as a different kind of hypervisor. And so, for instance, you come up with one. Let's say they have to execute instructions. It has to somehow jump to a VM exit trap handler. Great. Now you've identified some of the resources it uses. Find out how you, from your vantage point, can measure those resources. Can you measure it directly? Is there a register you can read on the CPU that tells you, hey, there are 22 TLB entries in use from your ACID right now? No, there isn't that kind of thing. But you can actually modify and measure the side effects of the processor in the microarchitecture state by doing things like measuring the branch target buffer by just having a series of loops and jumping to various targets in those loops. And the CPU, because of the deep pipelining, has a branch prediction buffer. I mean, you guys have read Tom's Hardware, right? You see, caches, branch target buffer, things like that. This is what makes your CPU go fast. A misprediction is very expensive in modern processors. You have a deep pipeline, and if you predict the branch wrong, you have to refill that whole pipeline before you can continue executing instructions. So in this case, you can measure those by saying, hey, is my branch taking a certain amount of time or less? If it takes too long, then you know something else ran, maybe an interrupt, maybe a VM exit, and it used some of the branch target buffer state because it made its own branches. It has to say if-then at some point in its execution. After you've done that, you found a way to measure it, you know what kind of resources you're measuring, then what you want to do is take as many measurements as possible and eliminate the jitter using basic statistics. But the important point about all this is we've talked a little bit about crypto timing attacks. Those are much more difficult to mount against systems than a simple single-bit extraction, which is, am I virtualized or not? With RSA, 1024-bit keys, stuff like that, you have to do multiple measurements and correlate them significantly to be able to eliminate some of that jitter and to be able to be sure you have the key right. Because if you guess a key half right, guessing 512 bits of a 1024-bit key won't do you any good. But guessing a single bit is a lot easier, and it's a lot easier to measure this state.
So now we want to give you kind of an overview of the next class of attacks that we're using to detect virtualized systems. We want to talk about vantage point attacks, and I want to give you a fairly straightforward example. Last year when we presented Vitriol and when Joanna presented Blue Pill, there was a lot of conversation about the x86 timestamp counter, which is a counter that increments with the frequency of the CPU. And the interesting thing about the timestamp counter is that it's a source of time that you get directly from the hardware. And like we said before, you issue a CPU ID instruction, which is a mandatory VM exit on VTX hardware, right? Well, you can time the length of time that it took for CPU ID to exit. It should take 200 cycles. You can measure that directly. Call CPU, get the timestamp counter, call CPU ID, and reserialize and call RDTSC again, and take the delta and see, did CPU ID take an unexpectedly long amount of time to run? That's an obvious problem with hypervisor malware, but it's also pretty straightforward to defeat. It's pretty simple, right? The VTX hardware, and presumably AMD as well, gives you the ability to offset the TSC to present kind of a coherent notion of time to the guest operating system. So you can offset it when you run, and mask the fact that the TSC, incremented much further than you expected it to run. So both Vitriol and Blue Pill take care of that attack. But there's a myriad of other time sources in your computer. Take the HPET, the high-performance event timers in the Intel chipset. There's an entire other alternate set of timers that you can talk to that Vitriol, at least, doesn't virtualize. It does not intercept attempts to read from the I/O mapped memory that the HPET resides in. You can read that memory and get a continually incrementing 64-bit timer that represents what time is going, how much time is elapsing on the computer. And if you don't intercept that, even though you've masked the TSC, you haven't masked the HPET. The two disagree with each other. First of all, the HPET tells you CPU ID is running longer than you expected it to. And second of all, the HPET is disagreeing with the timestamp counter. So if you forget to virtualize that, you have a smoking gun that you're virtualized when you weren't expected to be virtualized. Here's another one. The performance monitoring capabilities of modern Intel chipsets have performance counters for optimizing code and for compiler writers and systems engineers. And they count all sorts of different microarchitectural features. For instance, branch prediction misses. You can ask the hardware how many branch mispredictions there were directly. It's another counter that lives in I/O map memory that you can set up and then read from later. You can execute a span of code that includes VM exits because you've injected CPU ID or whatever into them, and then see if, when you execute CPU ID, that shouldn't actually change the number of mispredicted branches. It isn't a branch. It's talking directly to the hardware. But the branch prediction performance counters will betray the fact that happened because when you actually entered the hypervisor, you executed all sorts of code, which did perturb those counters. So if you forget to virtualize that, you're screwed up. And finally, there are things like the AGP GART. The GART is an alternative memory mapping interface for scatter-gather I/O so that you can present to your graphics chipset the illusion of a contiguous space of memory that isn't actually there. It's an entire other memory translation capability in the system. You can program the AGP GART to point different pages of memory to different other pages of memory. If you don't virtualize the GART, you can use the GART to scan direct physical memory instead of whatever the virtualization, the hypervisor, tried to pass off to you as actual memory. Again, we presented that diagram before of you have the instructions, then you have the CPU, and then you have the chipset below it. And virtualization does nothing to the chipset itself. It doesn't actually protect the chipset. The chipset isn't virtualized. There's no idea that you're virtualized. That's a transaction that occurs between the instructions and the CPU. So if you miss things like these I/O things, like the GART, which changes in different versions of the software, like my MacBook doesn't have a conventional GART, then you can use those to profile as well and get the hardware to betray you.
One thing here that's really important is he's talked about neglecting to virtualize it. But there's the other side, which is you go and you try to trap every single one of these things. And these are complex pieces of hardware. For instance, I would challenge anyone here to run an arbitrary piece of code, run another arbitrary